So, very good morning. Welcome you all, friends. So, from today's series of lecture, here we are going to, as per the syllabus, we are going to consider module number 5. So, the module number of 5 consists of the two important aspects of the network analysis. That is the graph theory approach. Number one, the graph theory approach to analyze the given network or the available network so that we can find out the type of responses governed by the assigned network or the dedicated network. Okay, as we talk about in the very beginning of this lecture series, that there are two different approach of analyzing the network. Okay, as far as the network analysis is concerned, and fundamentally we very well aware also that what is the fundamental difference between the network analysis and network synthesis, that we have discussed at the very beginning of the series of this lecture series is network theory. So under the head of this module number 5, we are going to discuss the graphical approach, the graph theory approach to analyze the very complex networks in real life scenario applications. Because as you know that the mathematical model based, the typical KVL and KCL based network analysis, as far as the transients is concerned, or applying the theorem to simplify the network is concerned, to find out a particular parameters or variable is concerned. Okay, or whether you talk about network functions or two-port analysis is concerned, or whether you are switching from time domain to frequency domain using Laplace transform and return back to the time domain using inverse Laplace theory is concerned. Okay, all these things you can do with some kind of simple or maybe moderately complex electrical network. Okay, but when it jumps to the hundreds of or the tens of the complex loop, and where each and every loop is again further interconnected or interlaced with the another or adjacent loops, it will be extremely difficult to write the equal number of mesh equations or the nodal equations to find out the proportional number of dependent variables. Okay, though it is practically possible, but it is a very time consuming process. And as I have been told you that the mathematical modeling is nothing but it represents not only the efficacy and the stability of the system that can be practically realizable or not, but the number of steps consumed during the mathematical modeling of a given circuit. It also indicates that how early or how delayed response you will get as far as that particular electrical or electronic circuit is concerned. That means if you are required to write down more number of steps or mathematical models, so it represents that you required equal number of steps. That means you have to write a heavy algorithm even if you are dealing that particular circuit with the help of some kind of software or firmware. So obviously the response of time of the circuit is always going to increase, and that is not at all a good signature as far as any stable and efficient electrical or electronic circuits are concerned. Fine. At the same time, if the number of steps are consuming is less, if it is reducing, so it indicates that the algorithm working behind of that particular mathematical model will also consume very lesser amount of time as compared to the any other complex models, and therefore you can avoid the delay response. So in this kind of scenario, the idea is to adopt the graph theory, because that is the very efficient way to replace the mathematical model based analysis and find out the analogy of a particular variable or the response of a particular variable as far as the overall circuit is concerned, or maybe across a particular source or elements are concerned. That we will try to understand in the following slides. At the same time, the second topic, which is a very brief one as far as this syllabus is concerned, we will also talk about around 1 to 2 lectures. We will dedicate for the designing of a passive type of network filters. Okay, so passive type of filters, that means it will be only a combination of RLC elements Okay, it will not involve any kind of semiconductor devices or the operational based amplifiers, right? So as far as these two topics are concerned, I would in fact suggest, okay, that here we talk about the module 5 and one more important aspects. Now, depending on the type of authors, okay, who basically write a particular dedicated book over the network theory or the various aspects of network theory, or whether you talk about your expert who is dealing with this syllabus related to the network theory. So there could be two possible approach. Though graph theory is also related with the network analysis, so maybe it stands two different popular approach rather than adopting or delivering the lecture in a serial manner from module 1 to 5. That is, like some of the authors, they have a flexibility, or some of the specialists, they have an option that they will consider first the analysis of coupled network, that is the fundamentals of network aspects and the electrical engineering, and the self and mutual inductance is involved in the electrical engineering. Okay, as till this point of time you might have understand the role of magnetic field, okay, is extremely crucial as far as the any electrical or electronic networks are concerned. Fine, because of its a typical nature. And then straight away jumping to the transient response, before jumping to the transient response, they generally believe to discuss the graph theory approach first and then jump to the mathematical approach, modeling based network analysis. Okay, that is from the transient response till you can say that your three-phase circuits. That's one way. Another way, maybe the instructors would be interested to go by the syllabus as far as module number 1, 2 and 3 are concerned, but then jump to the module number 5, cover up the graph theory approach, and then switch back to the graph theory and the filters aspect is concerned, because ultimately it is a part of the network theory, the network analysis, and then finally wind up the syllabus with the network synthesis, because you know that network synthesis is a completely a different ball game. Okay, the different aspects of the network theory than that of the network analysis. Okay, so I hope that now you will be able to understand that. Okay, that why at this stage we are going to discuss the network theory. Okay, though as far as this syllabus of BSSUT is concerned, we have a dedicated module as far as that particular lecture series is concerned. So again, like all other modules, here we are going to discuss the different critical and the fundamental aspects of the graph theory and the filters in the following 5 lectures series, and then followed by one lecture series we will dedicate it for the test and the doubt clearance sessions, including the first 5 minutes before sessions as far as the any lecture series is concerned for the doubt clearance session. Okay, I would advise particularly for this particular topic to cover, I think the better book, the options what you can have, the obviously the Robert Boylston, that is the circuit analysis. Graph theory in maybe Van Valkenburg is a very limited. So what I can suggest you that there are some other options like William Head's, that is the engineering circuit analysis, or you can approach the network analysis synthesis by the Coe, okay, Franklin Coe, or maybe you can refer the Huysman, or maybe Huck's electrical and electronic theory, that is also very good option. Even some of the Indian authors, okay, that is the Sukhija and Nagsarkar, published by the Oxford University Press, that is the circuits and network, is also a very good book for the graph theory that you can refer. Okay, though I'm not here encouraging to refer any particular book, it is up to you. Beyond the this recommended slide, you can also refer any book. And the A. Chakravarti of the circuit theory is also very good option as far as the network theory is concerned. In NPTEL slide, you can refer some of the dedicated lecture series available from the IIT Kharagpur's faculty as well through the NPTEL site, other than the MIT open courseware options. So these are the options you have as a support system, right? So as I said that in under the head of this particular syllabus, so we are going to at the end of the this module, we will be supposed to achieve the course outcome number. So let us here we begin that before going to discuss that how the network graph theory approach, graphical approach of analysis will help us to realize the any complex electrical network rather than adopting the typical time domain mathematical model based approach, or sometimes switching to the frequency domain approach, okay, to resolve, to get the response of the circuit, obviously in the time domain. uh, Before come across over this, as I said, that let us predefine some of the typical terminologies we are going to experience under the head of this particular topic. Fine. So that this standard nodes and the dashed line are okay. That the hard line are representing the configuration, the graphical configuration of a typical electrical or the electronic networks. Okay. So before going to understand this in depth, let us predefine some of the terminologies which will be come across again and again throughout the discussions. Okay. So sometimes we will come through a term that is the branch. So it is the same what we used in case of the mathematical modeling of the graphical analysis. Basically, it is a line which replaces one network element. So that means, for example, if you see in this demonstration, there is a node C and there is a node D. So C and D are connected through a hard line. So that means basically if you look at the original electrical network of equivalent which this graph is prepared or this tree is prepared, in fact I would say, okay, in that case the CD, the dotted line, two dotted lines are connected through a hard line. Okay, that is the mesh. So this branch is nothing but it is replacing or it is the reflection of one of the types of element or the source, including the source, including or excluding the source, participated in that particular network. That is called the branch. Okay. Note, as usual, it is the point of intersection between the two or maybe more than two branches. Okay. So what is the graph then? The graph is basically the symbolic representation, okay, using the merit of nodes and the branches as far as the any given electrical or electronic network is concerned. So it is very obvious that any electrical network may not be complete until unless it is not going to establish at least one or more than one closed loop, okay, which will ensure the return path of the current. So what if the node is open, like you can see in these diagrams as far as this slide is concerned? So it is called a tree. So now you remember that the graph and the tree are the two different terminologies related to the same electrical network. Okay, it is point to be noted. Okay, so what is graph we do understand, and therefore the question comes that then what is tree? Okay, so basically tree is an interconnected open set of branches. Okay, please be noted, this statement is an interconnected open set of branches which ensures, or you can say that that includes all the nodes of the given graph. Okay, that includes, point to be noted, all the nodes of the given graph. Okay, but there cannot be any closed loop as far as a tree of a graph is concerned. So that means a graph which represents the graphical representation using the branches and nodes of a given electrical network. Obviously, any network will always have at least one mesh, okay, one closed path or maybe more than one closed path. Understand? Because it will at least establish a contact with the lower potential, that is the ground, what we assume. Fine. So but as far as the tree is concerned, it is always a open-ended terminology or the representation of a given graph, right? So we will understand it in a more detail. So that means a tree, okay, have a more than one option. So that means there are more than one option to construct a tree of a given graph. So whenever now I will say graph, so that means that represents a equivalent electrical or electronic network. Okay, please be noted this. Fine. So where there are more than one possibilities of the to construct a tree, there are more than one way through which you can construct a tree of a equivalent graph or of equivalent electrical network. Right? So please be noted this. Okay. Now, what is the tree link, or sometimes it is simply called the link or the cord? Okay. Remember, tweaks are different. So tree link is a specific terminology, or in short, many times we called it link or the cord. Okay. So basically, the tree branches and the link together, when they participate, they complete a graph. So that means the branches, those are now kept isolated themselves. Those are not participating in construction of a tree is called the link or cord. Understood? Fine. So therefore, that means for an electrical network, if it is a representation of a typical combination of 6 branches, and let's say I would say that 5 nodes. So a tree will be a combination of a 5 nodes, but at least one minus branches. So that is 5 branches. And the particular branch which is not participating in the construction of a tree is called the link or cord. Okay. We will consider some examples. Okay. So that is the your cord or link. Okay. As illustrated in this figure. Let us try to extrapolate it in a more different way. So as you can appreciate in this particular slide, okay, so maybe the bottom one is slightly uh, invisible, you can say. So let me dictate, don't bother about it. Okay, so it is basically the conclusion of the previous slides. So as you can see that the tree has some following qualities, you can say. What is it? So it consists of all the nodes of a graph as we discussed. Okay, and the graph, if it has consist of n number of nodes, then the tree will consist n minus 1 number of nodes, okay, to establish a open path. Okay, because tree cannot be a complete path, where is a graph is a close-ended combination of the close-ended path, okay, of the branches of a given network. Okay, so there cannot be any closed path as far as a tree is concerned. Okay, there can be many possible ways to construct a tree as far as the graph is concerned, that I have been already discussed with you. So let us consider as an example as demonstrated in this particular figure. Okay, is again, that is, for example, now onwards we are going to consider the capital B, which stands the total number of branches of a graph, right? At the same time, the L is going to represent, capital L from here is going to represent the total number of links, and then the capital N is represent the total number of nodes participating in the graph to construct a graph or as far as the tree is concerned. So therefore the tree branch, the number of tree branches will have n minus 1 in numbers. Hence, as far as the links are concerned, so as we discussed in the previous slide, what is the link? Here onwards we stand is L. So L is equal to B, that is the number of branches minus number of links. Okay, to construct a trees, and how many links to construct a tree? So that is your n minus 1. So overall you will get B minus n plus 1. So that is the total number of links you can get. So as you can appreciate that if you will find the total number of links and the total number of branches participating in the tree, so you will be very easily able to find out the total number of branches participated in construction of the graph. Both will be equal. Okay, so B will be equal to L plus the total number of branches participating in the construction of the tree, that is n minus 1. Clear? So that is how, like in this demonstration, as you can see, that if the total number of branches are how many, here you can count, that is 4, 5, 6, 7, 8, 9, 10, 11, 12. So you see that here you have a total number of nodes are 12, where the total number of branches are participating as 15. So how many links you would have? That is the B minus n minus 1. So that is your 15 minus 12 minus 1. So you are getting actually 4 number of branches. Correct? So that is how you can find out. Classification of tree. So obviously the fundamental aspects are still remain same. We are still going to consider the mesh analysis, that is the Kirchhoff's voltage law, and the nodal analysis, that is the Kirchhoff's current law, to simplify or to construct any equivalent tree as far as the given graph is concerned, or in other words the given electrical or electronic networks are concerned. So from now onwards, whenever we are going to involve the mesh analysis, okay, into to participate in the graph theory, okay, to simplify the equivalent electrical network, that we consider we talk as the tie set of the network. We can talk it tie set of the network. Whereas whenever you are going to adopt the KCL approach, that is the nodal analysis, to simply to construct the equivalent branch, sorry, to equivalent graph or the tree of the network, that is typically is called the cut set method. Okay, so let us see one by one. So now first we are going to consider the tie set approach to uh, resolve the network or to find out the solution of a given network using the graphical approach. So as demonstrated in this particular very slide, that the given electrical network is given, and here you can appreciate that E of t is representing the instantaneous value of the electromotive force. The, in other words, the equivalent source is applicable to the entire electrical network. So obviously to energize the entire electrical network, so along with the two series resistances through both the polarities, and there are the couple of capacitive type of elements are also getting involved, and the couple of inductive elements are also involved. There is a load resistance, and as well as there is also another resistance which is participating into the network to connect the resistance and inductive network. Okay, along with that there is also a current source which is being applied. So it is a typical combination of uh, of an electronic network where all the possible passive elements and both the type of sources are involved. So let us see how this network. One way is that there are many possible way to solve this particular network. But remember, in a real life scenario, we are going to consider the tie set or cut set approach to deal with a particular network which have a equal number of the complexity or maybe very higher degree of complexity. As you can appreciate that as far as this particular circuit is concerned, there are many ways. So you can straight away apply the KVL. You can write out down the three nodal loop equations, and try to find out a solution of a particular requirement which is asked for. Or you can apply the source transformation technique to convert the one of the sources, that is the voltage source, into equivalent current source, and or the current source into equivalent voltage source by the transforming with the rest of the elements which is participating in that particular loop or across the loop, and then you solve it. Or the third approach here is that apply the graphical approach of the analysis. So under the head of this topic, as we discussed, that initiate our discussion, that we are going to adopt the graphical approach. Fine. So as I've been told you that if this is the given electrical network, so the first very thing is comes into the existence, that how to form a graph. So let us be define the element numbers, okay? Because in this demonstration, the specific element value is not given. Okay, so it's a kind of a generic problem. So it doesn't matter whatever the numerical value is. In any way, it will be a constant. So whether you talk about the resistances, inductance, capacitance, or voltage source or current source are concerned. So it's immaterial for us at this stage. Okay. So to bring more clarity for our discussion, so let us give a nomenclature to each and every node and a branch. So the assignment we have given in this way, that A and B is the node which is going to interconnect the one of the inductor. Then B is C is the followed by the capacitor. C and D are connecting your load resistance. B and E are connecting another inductor is participating into the network. E and F is the interconnecting another resistance. F and G are connecting the another participating resistance which is connected the lower potential of the voltage source, and the higher potential of voltage source is connected through a branch, that is H and A, whereas GH is representing the connection of the branch of the voltage source. So remember, whenever we are going to replace construct or the graph of a given tree, so there is an analogy. So what is the equivalent impedance of the current source? So it is a basically open circuited, right? Because it is a current source, that means the rate the current has a very high value and the voltage is very is low. So the equivalent impedance you are going to construct is a basically open circuit. What is the equivalent circuit of the voltage source whenever we are going to replace? So you replace it with the short circuit conditions. Okay, so that is it allowed to pass through it, whereas the I of t is basically indicating the blockage in one way, the sustainability of that much amount of current. So that is why you are replacing it with the open circuit, whereas the voltage source you are replacing the current source. Okay, fine. So now, and the rest of the elements, whether it is RLC, any RLC element is concerned, you are going to simply replace by a hard line. So there is no necessary that you follow the exactly the same replica. You can draw it in a freehand. Okay, you can draw it in a freehand. So for example, if I am going to demonstrate over here, and you want to interconnect this point, that is your G and H. Okay, so this G and H is going to replace by a, okay, so let's say if this is the point, so and this is the another node, or you can say that this particular node is G and this particular node is H. Okay, and I would say that this particular node is A. So remember, because of this voltage source, these two nodes will be short circuited, and the H and A consist of one element, so this node is finally going to be interconnected with the A. Okay, so equivalent of this will be equal to, you can say that there is a point, because there is a no element is participating between G and H. So the equivalent of this particular circuit, or I would say that if there is a node A, as we have mentioned here, and if this is node G, so it is straight away going to connect a line between G and H, which includes inherently the GH and plus HA, because GH is a short circuited terminal. So I hope you understand. Or even you can interconnect these two lines with some freehand diagram. There is no necessary that you draw in a straight line, because it is a tree, so it can have any variable shape, as you can see the natural reflection of the tree in our nature. So even you can interconnect like this, so there is no restriction at all. Okay, so I hope now you understand this. So rest all elements are replaced, and we also nomenclature, we have nomenclature the nodes, we nomenclature the branch. So the branch which is has been constructed between A and H is represented as the branch number 1. Similarly, A to B is branch number 2, B to C branch number 3, C to D branch number 4, D to E branch number 5, E to F branch number 6, F to A branch number 7, and F to G branch number 8. So here you see that as far as a graph is concerned, as you can appreciate that it is a closed loop network. It is still a closed loop network as it is originally reflected in the electrical or electronic tree. But you see there it is a mention a terminology that is called the oriented graph. Now what is the difference between graph and oriented graph? As the orientation says that it always demarcates a particular end of a flow. That means the direction of the flow, fine, of the network. So here we will obviously have our own freedom to assume the direction of flow of current, because at the end of the day it will decide it that whether your assumed direction is correct or not. With the help of magnitude you are achieving the positive value, your response, or your response in terms of the negative values, that is a 180-degree phase shift. So you still have that same flexibility, so you can assume in any direction wherever you want. Okay, so we assume the direction as shown in the figure B. Once the direction is you have been assumed or you fixed as far as the particular branch of the graph or tree is concerned, is basically is called the oriented graph. So if the direction is not given, then it is a graph. If the direction is already mentioned or you have been assumed, then it will be recognized as the orientation graph or an oriented graph. Now, from the oriented graph or from the given graph, whenever you wanted to construct a tree, remember the condition is still remains same, that as far as any tree is concerned, it should not have any closed loop. It can't have even a single closed loop, because remember in this original electrical circuit, we will replace the current source by the open circuit condition. So therefore, there is no branch between B and E which is interconnecting, but the G and H are already merged with the G and A. So there is a single branch. So now from this onwards, you can say that you have at least you have to open at least two branches. Either in this demonstration, it has a replace F and A. You consider as an open circuit. So that is basically link, and D and C, that is the branch number 4 and branch number 7 are considered as the link as far as this one possible type of tree is concerned. So see, remember it is here it is mentioned one possible tree. What you can do, you can open branch number 1, and you can then open any particular branch between 2, 3, 4, 5, 6. So it will also a way to create a tree. So from here you can probably you can find out that probability how many number of trees can be constructed from a given graph or from a given incidence graphs. Okay, so that what is incidence graph we will discuss a little later in the same lecture series. Okay, so from here, as you can notice that if for that particular given graph, even if you will consume the two number of link current, that is the mesh current, okay, just we consider in any KVL approach. So the analogy or the brief of the summary are as follows: the total number of branches are 8, the total number of nodes are 7. So obviously what will the total number of tree branches? So total number of tree branches will be always n minus 1. Okay, 1 less than the total number of nodes. So that is n minus 1 is equal to 6. So therefore now here 6 is the number of tree branches, whereas the number of links are these what you call number of total number of branches are the 8, total number of tree branches are the 6, total number of nodes are the 7. So from here, if you are going to replace the b is equal to 8 and n is equal to 7, so total number of links you are getting 2. So it's just such a justifies that you have to remove at least 2 of the branches to convert that particular graph or oriented graph into the equivalent. Okay, so that I hope you understand. So from this previous diagram, what you can consider that if your mass direction, if your assumed mass direction as flexibly we have been adopted is going to complement the direction of flow of current through the particular branch, then it will be represented as a plus 1. If it is indirectly connected, that means in opposite direction, if the direction of flow of mesh current is opposite to the direction of flow of branch current, then it will indicate by a negative of 1 minus 1. And if there is a no interconnection between a particular branch current and the link or the loop current, in other words you can say, then it is going to replace by the 0. So remember, these 0 and 1 are the only two magnitude which is being used to interconnect or to represent the die set matrix of a particular given electrical graph. So here remember we are adopted as we discussed in the few slides back that first we have considered the die set method, that is the graphical approach of to construct a tree, okay, or to analyze a given electrical circuit using graphical technique, okay, complement to the KVL, Kirchhoff's voltage law technique, right? So in the previous diagram, you must have noticed that what are the links? Branch number 4 and branch number 7 are constructing the link. Whereas the what are the number of branches you have? We have a total number 8 number of branches. So what you can do, you can horizontally arrange in the x-axis the number of branches 1, 2, 3, 4, 5, 6, 7, 8. Whereas the particular links what you are participating to construct or to write down your loop equations or your loop current, okay, that you can consider in the, your vertical axis, that is 4 and 7. Okay, so in this demonstration it is mentioned 7 or 4, it doesn't matter, fine. So if you consider 4, the direction of a flow of current of mesh current, or that is called your loop current, and the branch current in branch number 1 are basically same. So it is replaced by the plus 1. Similarly for the branch 2, 3, 4, 5, 6 is also favoring in the same direction, as you can notice. So all are replaced by the plus 1. Okay. Branch number 7 are not connected with the link or the loop current number 4. Okay, so therefore it is going to replace by the 0, whereas the branch number 8 is also favoring in the same direction, so it is referring as plus 1. As compared to that, if you consider the loop current 7, that the link current 7, okay, the link is 7 because there are only two links, okay, the branches those are removed from the oriented graph to construct the equivalent tree, that is the branch number 4 and 7. If you look at the 7, it is in opposite direction of the 1. It is not at all related to branch number 2, 3, 4 and 5 and 6. So it is replaced by the 0. 1 is in opposite, so it is going to replace by minus 1. 7 is favoring, so it is the plus 1. And the 8 is also opposing, so it is the minus 1. So that's how you can construct the die set matrix. What is in that case the incidence matrix? You will also sometimes come across the terminology that is called the incidence matrix. Okay? So incidence matrix is nothing but it translates the graphical data of a network. Okay, so what are the graphical data? Those interconnection points. Okay, we got due to the intersection, or you can say that which establish the interrelation between the link and the branch currents, or the loop currents and the branch currents. Okay, that graphical data of a network into the algebraic form. Okay, hence it is a quite important, it is a very important whenever you are going to develop the computer based algorithm to resolve any complex electrical network using the graph theory. Okay, so as we says that it is going to represent by only the two terminologies, that is 0 and 1. More specifically in terms of phase, it is 0 plus 1 and minus 1. Okay, which is used to denote or to completely define a particular oriented graph. Okay, so in other words, the oriented graph or the direct, sometimes it is also called the directed graph. So this relationship is going to prepare, or this going to be compressed, okay, or is analyzed, okay, or you can say that is accumulated, is a better term, with the help of the incidence matrix. Let us consider one problem. Okay, I would insist you that you try to attempt this problem. So this figure is representing, this is nothing but is the equivalent graph of an electrical or electronic network. So a simple problem is given. So your job is to find out the incidence matrix. So remember, the oriented graph is already given to you, and if not given, then you can assume your direction if the graph is already known to you. If the electrical network is given, then I have been already told you the way, okay, the method you will adopt, the procedure you will adopt to construct a tree into a graph, and then convert a graph into the oriented graph. So once it is done, then you can find out your incidence matrix. So in the horizontal axis, you are going to consider your number of branches, those are participating in the graph, okay, to construct the network, or sometimes it is also called the edges. Okay, similarly, the vertices is also a term which is replacing as the node. So you can, in the vertical axis, you can write the nodes or the link. Okay, so remember, as far as the incidence matrix, in the previous demonstration, we considered the interrelationship between the links and the you called the graph branches. Okay, the branches of the participating in the graph. As far as the incidence matrix is concerned, here we are going to establish the interrelation between the number of nodes are participating and the number of branches are participating. So from here, in this bridge network, as you can say, for example, branch number 6 is nothing but it is representing the equivalent voltage source. Okay, branch number 5 is nothing but it is representing your load impedance of the network, and four arms of the bridges 1, 2, 3, and 4 are representing the balance or unbalanced combination to construct or to find a particular electrical bridge network, which is sometimes is primarily used as a pre filter, okay, before going to process this electrical signal to bypass the noise or to increase the gain of the circuit, okay, as an instrumentation amplifier. So as example is instrumentation amplifier is nothing but it is an example of a pre-filters, okay, using the bridge network. So in any instrumentation amplifier other than the sensing network, the very first stage what we use is always the bridge network. So bridge is very popular. Okay, so here that particular problem is given. I suggest you to construct the equivalent incidence matrix of this particular graph. So I hope that you will be able to do it, okay, as shown in this particular demonstration, and do not find any difficulty. Just for your flexibility, I have been mentioned that let's say if any current is going away, so you can indicate by the minus one as from the particular node. So for example, there is a node E which is participating over here, there is a node A. So any current is going outward is going to represent by the minus one. From is anything is incoming is going to represent by the plus one, and if it is not related, it is going to consider zero. So there is another analogy also, because current is representing the electron is representing the negative of the polarity, and the direction of flow of electron is opposite to the direction of the current. So the direction oriented graph is representing the direction of flow of the branch current. So that means direction of flow of electron is in principle is opposite. Okay, you may or may not follow in your analogy, it doesn't matter. At the end of the day, you will get your equivalent response through the graph theory. But that is the standard analogy. So in that case, so that means the electrons are flowing from the terminal from node B to A. So that means now is going to be A is going to be more and more negative as compared to the B. So therefore any current is flowing out is represented by the minus one. Sometimes author consider exactly the reverse scenario. Any outgoing current is representing the that it is flow of current is always from the positive polarity to the negative polarity. So it is considered a plus one. It is incoming is considered as minus one. Okay, so it is up to you. At the end of the day, what the common thing is that whether you consider the standard analogy or the assumed analogy, as some of the electrical or electronic science experts insist, in both the way. Okay, if you establish the interrelation of this incidence matrix, how do you come to know that what the solution you have been find is verify that it is correct or not? So here I will tell you that how you can verify. There is a very simple approach. If you are going to add the total numbers in any vertical sections, which is interconnecting the participation of a particular branch with the all possible nodes of that particular electrical network, that sum should be always zero. Okay, so there are four nodes, that is A, B, C, D. Those are, and we try to interrelation. We try to see that the interrelation of the participation of the particular branch current, okay, that from the branch number 1 to 6 with respect to each and every node. So that's how you are getting these vertical numbers. So for example, if you are going to consider the branch number 1, you are getting the value minus 1 plus 1 0 0. So if you are going to add all those numerics, at the end of the bottom you are getting 0. Similarly, from 2 you see this is 0 minus 1 plus 1 0. So if you are going to add all these numbers, you will always get 0. So through this you will be able to verify that whatever incidence matrix you have been prepared, whether that is correct or appreciate it. Let's see, we are going to consider a particular example of the tie-set network. Let's see that how the properties of the incidence matrix. Okay, what are the properties of the incidence matrix? So there are two possible, two important aspects or the properties of the incidence matrix. First, the determinant of the incidence matrix of a closed loop is always zero, as I've been told you in this demonstration. Okay, that the determinant, if you see, if you are going to add all those, okay, the vertical numbers, which is going to establish a relation between the node, okay, all possible nodes ABC with respect to the given branch, that sum should be always zero. So that first, at the first step, it is uh, indicating that the incidence matrix you have been prepared with respect to the oriented graph, whether it is a correct or not. Once you have prepared it, then you find out the determinant of this particular matrix, and the determinant of this particular matrix should be always zero. So if it is a zero, so then you can say that basically it is one of the property which ensures that the incidence matrix what you have prepared is mathematically or is absolutely correct. Number two, algebraic sum of the column enters of an incidence matrix is zero. So that I have been already discussed. Okay. So one more demonstration is given. Draw the oriented graph from the incidence matrix. So remember here what the demonstration is given. There are 7 branches, and then there are these 4 nodes. So 4 nodes you can invariably anywhere you can plot A, B, C, D. Okay. So from here in this demonstration, what we consider that any outgoing is minus 1, any incoming is plus 1, and if it is not connected, it is 0. So sorry. So if you interconnect the branch node number A with the branch number 1, so branch number 1 is plus 1, so it is indicating plus 1. So you can first given the nomenclature, okay, it's up to you. So not at all bother that which number you are assigning. It is not at all necessary you will follow in this direction. So your branch number 4 in this demonstration can be your branch number 1, the branch number 6 can be branch number 5. So it's immaterial. Then, if you consider the branch number 1, whatever, like in this demonstration, it is considered the branch which is linking the between node C and node A. So for A, it is plus 1. Okay, so the direction of current towards the A should be there. Whereas if for C, if you see, it is the minus 1. So that means C is indicating that current is leaving. Right? Similarly, for the branch number 2, B is incoming, whereas the C is outgoing. So that means there is another direction of current, okay, the branch number 2, which is indicating where the direction of flow current from the node number C to node number B. So that's how we can prepare your the reverse thing. You can prepare if the incidence matrix is known, then you can prepare the oriented graph. Once the oriented graph is there, you can talk about the equivalent value of the element or the source participating in that particular network. Okay, we have been also discussed that how you can uh, find out that what will be the total number of possible trees you can construct from a given network graph, from a given graph or the oriented graph. So one way that you try to manually find out the try probability that how many trees you can consider, but it is this approach could be a manual, and number two is a time consuming, may be suited for a very simple electrical network which consists of maybe two or three meshes. Okay, but still it is a time consuming. But imagine there is an electrical network which is a combination of 50 different meshes and maybe 20-30 nodes. Then in that scenario, what you will do? So it's always better to approach the mathematics. That is, in this case, the incidence matrix based approach. So what you can do that first of all, you construct the incidence matrix of the given oriented graph, and from there you can work out the incidence matrix. So once the incidence matrix is known in this particular demonstration, so remember that there is always a node. There is one node is always considering as the what you call connecting the ground potential, that is the lower potential of the terminal, or in other words which provides the return path. Okay, to complete the cycle or to complete the loop of the electrical network. So you can probably even you can remove that particular node also to simplify even further your matrix, that is the incidence matrix. So sometimes it is also called the reduced order matrix. Remember, like in this demonstration, as you can see, okay, the A is representing basically the incidence matrix, but whereas A subscript R is representing the reduced order incidence matrix or reduced incidence matrix. Okay, so in this demonstration we have been assumed that node number C, which is participating over here, is basically connected to the ground terminal, is the lowest terminal, and we are going to remove this in the participation. So rest you have only two terminal, that is A and B. So if A of R is basically nothing but it is a 4 cross 2 matrix, so in that case A of R transpose is basically the transpose of matrix will be 2 cross 4. Okay, the reverse, right? So in that case the number of possible of trees can be constructed will be that noted down. It is the determinant of the reduced order matrix, incidence matrix, and the product of the transpose of the reduced order matrix. So the reduced order matrix is already known to you. You have been constructed. The transpose of the matrix already known to you. So if you are going to find out determinant of these two, so from there you will be able to appreciate that there are five different possible way to construct a tree of this oriented graph or the electrical network is concerned. Okay. So I hope that you are able to understand this, okay, and apply the same theory in the different sort of problems to simplify the network. Let us proceed. So see, these are the five different demonstrations. As you can see, there is no sixth option. Okay, so it justifies our analogy. Fine. Let us move ahead. So in today's lecture, we discuss the about the different terminologies about the graph theory. That is the tree, graphs, oriented graph, incidences matrix, the nodes, the role of the nodes, and then the two way to classify the graph theory approach to resolve any electrical network or to identify any uh, dependent variables or parameter of the network, that is the die set and constraint matrix. We also see that how to prepare an incidence matrix, how to convert a graph into orientation graph, how to construct a tree, and then followed by how to prepare an incidence matrix for the given graph, which establishes the relation between the number of nodes and the number of branches participated in construction of a graph. So in the next lecture, now one by one, we are going to discuss about the die set and cut set method, and how these two methods will be helping to analyze the complex electrical network using the graphical